See what we can do here. There's a lot of empty space. There we go. That's a little better. I'll get up here. I should turn this around. I wish there was a, oh, I can switch my camera. Hello.
Hello, can you hear me?
I can.
Awesome.
Welcome.
Do we need a video or are we good like this?
You are free to do as you choose. It is always a pleasure whenever I get the chance to see the crowd. If you want to turn your camera around so that the other folks can have the experience of seeing the other. Yes, right there on her. Absolutely. Zooming in.
They are. See, just to let you know, there are people in my room.
They're eels. All right. Well, I can return the favor here. Hold on. Let me see. Surface camera rear. Oh, yes, we'll do the same.
Hey.
Oh, wait, there's one down here. Oh, and there is a crowd. We are all here. I know. Okay, wonderful. Let's admit folks in.
Good seeing everybody's smiling faces. Huh?
It is wonderful. Thank you guys for joining in. So we look like we are waiting just for spot C, maybe. Is that all we're looking for here?
They don't want to hear our
No, yeah. I'm trying to mute y'all for a couple of weeks now. I'm just kidding.
Better go get it. I'm gonna eat it. Okay. While we are waiting for 1, 2, 3, while we're waiting for anyone else who wishes to join in today, let me flip my camera back around and I'm going to do a very brief welcome to dual enrollment chemistry and your opportunities to learn in a somewhat familiar, maybe it was an unsettling time in the past, but we'll revisit that in a new dynamic because we're all together. My name is Mr. Garrison. I am one of the few. Now we have a bunch of us, which are doctors. And so we need to get familiar with some of the faculty that you're going to be seeing in and around these broadcasts. And so if you wouldn't mind taking over, turning on your camera on yourself as well as your microphone and introducing yourself here very briefly, that would be wonderful. So everyone gets experience and then we'll talk about what we're going to do. All right, head off. Microphone. There you are. Yes.
Me?
We're having a few technical difficulties. My name is Dr. K. I'm at Colonial Forge. Yes. So hi everybody. That's all I got for now. So
wonderful. Thank you very much. All right. Dr. N. Go for it.
Hey, I got it right. Hi, Dr. Newsom. Thank you.
That's it. Okay.
Have a good
Best
one.
wishes, huh? Keep it simple. All right. Miss Pogue.
I'm a man of few words.
That's okay. My words don't matter when I talk, so. Oh, which side are you at? Let me see your shirt again. Dr. Newsom.
He's at King George.
No, I know the kids don't. All right. Go ahead, Miss Pogue.
I'm Mrs. Pogue. I'm at Stafford.
Whoop. All right. Anyone else? Is that it? Is this just this? Oh, there's Miss Grigsby. Hello. Connecting to audio. It's almost there. We got one more moment here. Hi, Miss Grigsby. Welcome. So you are wearing 2 hats this year, and we have just gone through we've just gone through the field here, introducing ourselves very briefly. If you wouldn't mind to do the same and tell us what site you are also at and why you are wearing 2 hats this year, or how you are wearing them.
Hello, can you hear me?
Yes.
Great. I am Mrs. Grigsby. Hopefully you all know that if you're juniors in the program. And I am currently the DE chemistry AP Biology for CGS, as well as a section of AP Biology for Spotsylvania High School, because we don't have a teacher yet. So we did hire a teacher at Spotsy. Their current school won't let them out of their contract. So I am here until either that teacher is released from their contract or Dr. Peppers is able to return from his retirement to fill in. So right now I am doing both my director job as well as teaching all these fine human beings here at Spotsylvania. They are fantastic. So welcome to the new year.
Woo woo. Absolutely. Thank you very kindly. All right. So we got a pleasure of a special guest and a teacher. That's very exciting news. Okay. We only have about somewhere in the neighborhood of 30 minutes today. So what we are going to try and accomplish today is to get you through the next pieces of information that we need to address in this current unit. So if you wouldn't mind, I have sent tight here. Hold on. Let me see. They're saying we got some folk in a waiting room here. Let me see where they are, participants. I don't see a very top. Ah, it's bleeding in. Thank you, Miss Diaz. I let her join. She said she's joining. Oh, she's joining twice. All right. Well, when Miss Diaz does get in here, she is from the North Side. There you are. Oh, you better turn that camera back on. This is not the pandemic any longer. Microphone on as well. Miss Diaz, turn that camera back around there, swing it around. Introduce yourself to everyone, please.
I would be glad to. So welcome to, whoopsies. Apparently I can't turn cameras on. I'm having technology problems today. Hi, my name is Miss Diaz. I am here at North Stafford with my wonderful 20 gang. I'm a graduate of CGS class of 2007 for those of you who didn't know that. And here is.
So proof positive, you can survive and go on to become something reputable. Look at that. Awesome news. Okay. So here is what we are going to try and accomplish today. I want to talk about the atom. The atom is fundamental to our understanding of chemistry. I believe that the majority of today will be somewhat of a review. So what we're going to do to help it along, to break some ground, is we're also going to incorporate a little bit of historical information. Let me drop down these people here down to the bottom. And that away, then we could see the content. Okay. Oh, except for, let me make it full screen here. Hold on just a second here. And then. All right. Now we're ready. Okay. So what we're going to try and accomplish today is getting to know the atom, and we're going to do it in the form of a little bit of a historical discussion along the way. Okay, so what everything it is made up in the universe, whether or not you believe it, all material is made. Why is it doing it in that form? Hold on, let's just get out of that. Let's just do it this way. Is made up of matter. Matter is anything that takes up space and has mass. Now you can organize matter, and you can, oh, by the way, all of these notes have been shared with your teachers. So there is not a necessity for you to jot down every vital word that I'm saying. You can look through these notes at your own leisure, and you can try and grab some of the more pertinent information as we go along. So don't stress about if I seem to be going a little fast. Some of this content is not quite as necessary as I will slow down whenever we get to some of the really, really important content. So matter can be divided and classified into two big groups. We can talk about it as being a pure substance, which is where we're going to focus today. And then you could talk about mixtures, where we will head towards as we start combining these pure substances together. So pure substances means it's all the same material, which is what an atom is. An atom is the basic building block of matter. Now, we have known about atoms for, somewhere going on 2,000 years. Democritus is the first person. Now, there is debate as to whether this is an actual individual. A lot of this happens in some of our Greek literature, or if this is a combination of individuals. But Democritus is given credit for the first person who theorizes the idea that there are small building blocks of matter that can be combined together to make everything that we know. It wasn't until later on, about 100 years later, that we have Aristotle come along, and he believes, well, I'm going to specify what those building blocks are. He says, oh, well, they're going to be earth, wind, and fire. And you might say, no, not the band, just the elements, the basic elements of everything that he saw around him. And he says that if I just combine these in a special way, if I had the right instruments, I could make just about anything that I wanted. 2,000 years later, fast forward, and we start to understand science, and we start to want to investigate what things are made of. And so we have Robert Boyle, who comes along with scientific experimentation, and he starts to formalize how we are going to establish what matter is made of. He starts to parallel this to what we know in the body. And so corpuscles is what he's thinking, little parts of our body is how he's envisioning matter can be combined together to make a whole system. Lavoisier, in the 100 years later, right before the French Revolution, he starts to come up with this idea, however, that we cannot destroy matter. He is conducting a series of experiments where he is actually isolating elements. And so he has discovered about a dozen elements at this time. And so he is starting to think, well, maybe I should organize it. As we start to investigate the history of the periodic table, you'll note that his name comes up a second time, because he is actually going to create our first list of periodic tables, since at the time he discovered the majority of them. So he comes up secondarily with the law that you cannot destroy, nor can you create matter. So he says, if I start with, in an isolated chamber, a combustible material, and I confine all of the ashes and all of the gases that are produced, it's going to weigh the same thing. So he has the law of conservation of matter. So we're starting to develop what everything is made up of. And this is echoed in this one experiment here. If we were to take 612 grams of calcium carbonate, and then we had calcium oxide as one of the products, well, we would want to know, well, how much carbon dioxide could you actually have left over predictably? And you would find that it'd be 269 grams of carbon dioxide. It's all going to add together. Just because we don't see it doesn't mean that we have not created a new matter. So that was something that they had to get over with, so that they could start then isolating their elements. We have Joseph Proust, about a dozen years later, and we have the law of definite proportions. And what he is saying is that all matter, if we have a pure substance, is going to have the same ratio. So because of the previous experiments, we were able to understand that if we heat up some of these compounds, they break apart into their fundamental elements. This is how they're starting to isolate elements. And they found that the weights of these elements were very consistent. So he comes up with the law of definite proportions. We could expand upon this one. We always talk about there is a, what is your body made up of? You hear some wild ratios that we're 90% water. Reality is we're probably somewhere in the neighborhood of about 75% water. And even at that, it would be hard to isolate it because oxygen is so fundamental in many of the compounds that are ingrained in us. The hydrogens are a part of much of our organic structure. And so I think that it's probably a little hyperinflated that we're made up in that 90% range. Okay, so definite proportions leads us to the law of multiple proportions with John Dalton. Here is the first person. If I were one of you who is trying to jot down some pertinent information, I would want John Dalton. This is where we start. He is not the first person, as I have already laid out, who's talked about elements and atoms, but he is the first individual to publish his work. So he has the atomic theory as his note in history, footnote in history. So we're in the early 1800s, and he has proposed 5 postulates that become somewhat significant as we're moving forward. He is saying everything in matter is made up of tiny atoms. He's saying that these elements that we are discovering have a fundamental building block made of atoms. And every atom is identical to the next atom as long as they are the same element. But if they're different, well, they're going to have different structures. He, of course, didn't understand what they were all made of yet. So we'll get to that here in just a second. And then he starts to some of the ancillary details of it. He says, well, if you combine them together, you can make compounds out of these atoms. His model is so simple. It looks like a gumball. It looks like a bowling ball. He is just theorizing that the atom is a solid sphere. Well, he was wrong. But that's okay, because he didn't have a whole lot of instrumentation or experimentation to get through this. So it wasn't until 100 years later that J.J. Thomson, after we had started to understand what electricity is, that we could start to excite some of the gases that we were trapping in these experiments. So we take for granted that there is neon in the open signs. What neon is a sealed glass container with trapped inside of it a specific gas. We call it neon generically, but it could be a different gas. And if you excite it, if you put electricity into that tube, it will cause the gas to light up. We'll explain that, why that happens. And if you were to put a magnet in next to that glass tube, it's going to cause the light to bend. There has to be something in that gas that is attracted to the magnet. So that got him thinking that there must be a particle inside of the atom. And that's why J.J. Thomson is given credit for discovering the electrons. Now, he was wrong too, because he theorized that the electrons were just inside of this solid sphere. He calls it a plum pudding. You and I, we might today call it a blueberry muffin. If you can imagine a solid sphere and trapped inside of it are all of these blueberries, then you have the idea of what J.J. Thomson thought our atom looks like. Oh, by the way, that's the second big scientist that I would write down. So we have Thomson, and I'm sorry, we have Dalton and we have Thomson. So we're building on 4 big scientists. Those are the 2 ones that I would really want you to emphasize on. Another experiment comes along, and it's called the Millikan oil drop experiment, named after Robert Millikan. And what he did is he built upon Thomson's understanding of the electrons, and he isolated these electrons. He was able to actually, through a very ingenious, which I can't even begin to understand how he could theorize this, he slowly drops oil through a hole and electrifies it, and then he is able to cause the oil to levitate because it's being held in an electrical field. And so he's able to measure and observe these small amounts of oil, and he can then quantify what the charge is associated with holding them in this electrical field. So we were able to get the weight of electrons, we were able to isolate electrons, we were able to get the charge of electrons through this experiment here in the early 1900s, late 1900s is what we're talking about. So along with that idea, now comes the third scientist that I think is very important to our discovery of what the atom is made of, is Ernest Rutherford. Ernest Rutherford comes up with the idea of the nucleus. So up to this point, we have Dalton with the atom, we have Thomson with the electrons, and now we have Rutherford, who does an ingenious experiment as well, looking at trying to disprove what has already been known. But in fact, what he discovers is that the atom is made up mostly of hollow material. He expected that if he shot radiation at atoms, that it would bounce back at him. That sounds a little silly to do in the first place, but what he discovered is that the radiation passes through the atoms. And the rationale behind that is because the atom is mostly empty space. But occasionally there'd be a few deflections, so it had to hit something. So his theory is that the atom has a solid core we call the nucleus, which is comprised of the protons and the neutrons, and then the electrons must be surrounding it. And this is getting closer to what we understand the atom looks like today. The fourth individual that I would implore you to want to know is Niels Bohr. So a couple of years later, he does an experiment where he also starts to bend light. He takes light and he moves it through levers, and as it moves through the lever, it tends to bend around. So there had to be some attractive forces where it's attracting to these levers. But what he discovers in it is that he actually separates the light into a rainbow. You and I take it for granted that we see rainbows up in the air. The raindrops are circular in nature, and it takes light a different time to move through that circular raindrop. And so we see a spread of the colors. Roy G. Biv. Well, he repeated that experiment, and he now says, okay, the electrons aren't just simply housed around the nucleus, they're organized in what we call energy levels. The higher the energy level, the further the distance. So the more energy it has, the further it gets away from this center of solid cores of protons and neutrons. So in summary, what we need to understand about our atom is that we have a nucleus, which is the proton and neutron. It is surrounded by electrons, which are organized in these energy levels. As we develop later in this unit something called the electron configuration, all of this is going to start to make a whole lot more sense. And we're going to couple it with your fabulous periodic table. So as the periodic table sits today, it looks like it's organized simply by either mass or by the number of protons. But we're going to actually find out that there is some hidden information in here about the organization of the electrons as we move along. So this is everything that I want to share with you today about the history of the atom. Now I've got a few more minutes here. I want to talk about what you're going to run into on that periodic table. You're going to need to become familiar with a couple of terms. The atomic number, going to be so important. You're also going to see on that periodic table the atomic mass. Now, those two are vital to us to understand. Most important of these, I think, is the atomic number. You have to know the atomic number of any element tells you the number of protons. Majority of the time, it's also going to tell you the number of electrons, but we can't rely on that. We're gonna alter that here in a few days, a few weeks, maybe. But we need to understand atomic number is the number of protons. So as I am looking at one of these boxes, the individual boxes off the periodic table, you'll notice in this example, it's in the upper left-hand corner. Periodic tables vary in their structure according to the authors. Just look for the whole numbers. The whole number values are the atomic numbers. They may be resting right under the symbol. They may be up in the upper corners. I'm not certain where they will be. But you need to look for the whole number, and that is telling you the number of protons that are in that atom. It distinguishes that atom from a different element. If I were to look at carbon, it has 6 protons. Oh, let's take a look at that. If I were to look at carbon, it has 6 protons. It's the 6th element on the chart. If I were to look at its neighbor right next to it, nitrogen, N, it would have 7 protons. If I look at the neighbor to its left, that would be boron. It has 5 protons. The second term that I just talked to you about is the atomic mass. It's important that you understand how it came about to a decimal. It is not, as you have been told in middle school, the sum of the protons and neutrons. That would make it a whole number. So there's something else going on that helps us to figure out the average. I think you should liken this to how you would calculate a grade if you were to have weighted grades. Now, we're trying to walk away from weighted grades in any of our courses, but I think you are familiar enough that if you say that homework is 50% and you make a 100 on it, and your tests are worth 50% and you only make a 70 on it, you have to average those two weights together to figure out what your final grade is. And that's sort of how we're going to come about these average atomic masses. Okay, so let's investigate then what an isotope is. This is fundamental to us understanding this average atomic mass. And then I'm going to have a participation portion for you guys just very quickly. You're going to practice this just a little bit. So we have atoms, we have elements, which are pretty much the same thing. Now we have this variation on atoms and elements. They are called isotopes. Just like you want to believe that you are very unique and very special. If you ever take the chance to Google yourself, find out, see if you are the only one of you in the world. Unfortunately, I believe that I was special and unique myself as well. And I Googled Trent Garrison, and there are, I think, last count, there were 6 of us. And the crazy thing is, 3 of us idiots became teachers. It was really crazy. And so there are 3 Trent Garrison teachers in the world, but none of them are as charming as I am. We're all different, and so are the atoms. Each one of the atoms are different, and when they are different, they're called isotopes. So the Trent Garrison who lives in Indiana and teaches economics, he's my isotope. The lesser isotope, but he's an isotope of me. And so if we have elements that have different numbers of neutrons, I cannot change the protons. If I change the protons, I change the element. The atomic number dictates what element you are. But if I change the neutrons, I simply am changing my weight. That's all you are changing when you change your isotopes. Everything else must remain the same. But by doing that, you actually, again, change the mass. And so we have to rationalize that and say, well, in this sample of all these different sodiums in this, we're going to have to average their weights. Well, we're going to have to know the percentage that those weights, that those isotopes exist in nature. So if sodium 23 were to exist, say in a 50% ratio, well, I can't write upon this screen. So if I were to say that 50% of my sodium were from isotope number 23 sodium, and 50% of my weight for sodium 24, well, then it's a very simple calculation. You just divide them by 2, and you add them together and divide them by 2. But if they're not, we're going to have to come up with a way to actually calculate that. And so what we need to be able to do is utilize a formula. I believe I have the formula. Well, I don't. Let me go to a different screen here, and I'm going to write down this formula for you here so we can figure this out. Okay, so if we were wanting to calculate an average atomic mass for any element, what we're going to need to do I do understand that the Trent in, did I say Ohio? In Indiana, Ohio, wherever it was, that he has a much better handwriting than I do. I am the sloppy one. Forgive me. I'll work upon that one. So what we're going to need to do is for that sodium 23, we are going to need to multiply it by its percent composition. What is its percentage out in nature? And if I had sodium 24, we would multiply it by its per specific percent composition. And if I had a third isotope, let's say we had sodium 22, well, I would multiply by its percent composition. So let's go ahead and fill these in here, and then we
Mr.
can do it.
Harrison,
Yes, did I not share
Okay.
that screen? Is that what you need?
yes.
Perfect. Let me do that real quick. Sorry about that one, folks. Oh, I've only got it specific to that one. All right, here we go. Got it. Thank you. All right, here we go. So on my average atomic mass, if this is what I am looking for, is to try and calculate what my average weight is for this particular element. In theory, this should come out to be the weight that is on the periodic table. So I'm going to say that this is about 90%, this is about 5%, and this is about 5%. So the math associated with this is that we will take the mass number. By the way, I need to have dictated that one. I'll get to that one. This value here, this isotopic value, we're going to multiply it times the percentages. I need to take a step backwards. I will take a step backwards and explain those values 23, 24, and 22. Just follow me on the math here real quick, and then I'll take back to the mass number value here. So if I'm going to put this into my calculator, I'm going to take 23 times 0.9, my percentage, 20.7. I'm going to take 24 times 0.05, my percentage, and I'm going to take 22 times 0.05, and I'm going to take 1.1. And if I sum those together, what I end up with is 23 grams, essentially, or 23, which we'll see. Now, if I go and look upon my fabulous periodic table, get this back here. The weight of sodium, it is difficult for me to show you here, but you can look upon yours in your classroom. It is 23 as well. This is how this value comes about. It is a weighted average of all of these masses. Now, that said, I need to take a step back and we need to talk about the mass number. Okay, so the mass number, let me see if I have it. There it is right in here. The mass number, this is another key feature of what we are talking about, is the sum of the protons and the neutrons. That's the difference in the isotopes, is this mass number. This needs to become distinguished from the average atomic mass. Folks, we have a lot of conflicting terms. They sound very similar. You're going to have to get them straight. Please do not just make a mistake of confusing atomic mass, atomic number, and now I'm throwing on top of this a mass number. I need you to please make note of those three terms and be able to easily distinguish them from one another. Okay, so really quick before we leave out, this is the last thing I want to share with you. So I'm going to ask you folks to play along with me with this mass number. Let's see if we can figure out what this symbol is and what its mass number is. So what is the element we're talking about and what is its mass number? I'm going to cut these out so that I can write on these. So give me a second. So you can see here, Riverbend, yours is the first one. You were trying to figure out what is the element and what is its mass number. And then we will record what they are for the whole group. Colonial Forge, same thing. You've got the second one. North, I'm not sure you're with us any longer. But King George, you've got the fourth one. Spotsy, you've got
North is here. We can do it.
Wonderful. Oh, yeah, okay. So your day didn't get cut short. Great. So
Well, it did, but travel bus didn't go, and we have Wolverine Hour, and my lovely juniors volunteered to keep themselves here.
well, and they're probably like, why did we do that? We should have left her. Anyway, okay, so grand. Each one of us has our own here that you guys can try and participate in. I'm going to give you 1 stinking minute, and then we're going to come together. Let me cut this out. I'm going to put it onto my other page so we can manipulate it. So hang tight. Let me cut this out. Did any of you guys out there teacher-wise, did you have your hard restart on your computer this morning? For it was because of some other reason.
Oh, indeed, yes.
Yes. Okay. So I had all these nice windows open and ready to go, and I come back to them. Now they are not there. So that's why we're a little bit messed up here, because they all kind of disappeared in between them. All right. So here we go. Let me create a new page. We're going to start with Riverbend. All right. So I need you guys. I need a volunteer out here in the audience to tell us what the element is first, and give us a brief explanation how you knew that that was the element. And then what we can do is then work on what is that mass number that coordinates with it as well. So who is going to be my volunteer here at Riverbend? What'd you say, Hannah? Bring it on. All right, she's got our first one. What is the element that we are looking at? It is arsenic. Now, how did you know that it is arsenic? AS. And that is the atomic number. So how did you know the atomic number for that one? That's exactly right. You've got to be able to associate the atomic number is the number of protons. It is AS. All right. So what is going to be my mass number associated with this one then? What, Emma? 87, she says. That is correct. So my isotope name is going to be arsenic-87. Now I've just put a symbol here, but it would be the full name. Let's see if I can spell it. Arsenic 87 would be correct. Great news. All right, Colonial Forge, following along that same logic. Let's see what you can do here really quick. Find yourself a volunteer.
Okay, Colonial Forge volunteers, Hannah here in the front.
Okay, so our element is Bi because the protons is 83, and then we take our neutrons, which is 124, subtracted by our protons to find our number on the side, which is 41. So it's Bi-41.
All right. Anyone want to help her out with the subtraction? Because that is what we do whenever we are given the mass number. So does anyone want to help her out and get the logic a little more solid there?
No,
All right, instead of subtracting, we need to add.
so then what is it?
Are they?
So what's going to be that mass number now?
207.
That is correct. Now, this is a secondary way in which we can express our isotopes. We can write it out with a dash and have the mass number, or we can write it out as a nuclear symbol and have in the upper left corner that mass number on the bottom would be the atomic number. Good job, Colonial Forge. All right, North, what do we have here? Now, we've got a scenario where we're going to have to deal with it because I didn't give you the number of neutrons. So North, this is your chance to shine.
All right, all right, guys, start with what it is. Who's my volunteer? Go ahead, Aaron.
The element is vanadium.
Vanadium.
Mhm.
And what's our mass number?
54, which would
Oh,
make-
it is.
which would make
You
the
were-
neutron count 31.
Oh, you went one above it. That's awesome news. You actually then went ahead and calculated, you subtracted, just as Colonial Forge had done before. You took the mass number, subtracted the protons to tell us the number of neutrons. Great job. King George, oh my gosh, they've shown you the path. Let's follow it. Do the same thing. Tell me what your element is. What is your isotope you just got us?
Vanadium 49.
Who?
Vanadium 49.
Not close. Rubidium. Rubidium 49. How many neutrons is it, sir?
Well,
Well, you sound that excited with that one, but yes, you're absolutely correct. Good job. All right, Staff Ford, let's continue with the successful round. Let's see what you can do. Tell me what is our element we've got going with this one? Because this time I didn't give you the protons. Oh, no. Are they there? They've left. Spotsy? It's up to you. Save us.
We're here.
Bring it on. Tell us what this element is, because I didn't give you the number of protons. That's going to be problematic, I bet.
Okay, the element is zirconium, and we took the number of neutrons and subtracted it by the atomic mass of
That is-
92 to get the atomic number 40, which is zirconium.
That is correct. Okay. What is going to be my mass number that goes in the upper right corner?
92.
Upper left corner, sorry, 92. That is correct. All right. That is absolutely correct. Great job, team. Okay. Your teachers are going to take over from here. They're going to clean up my mess. They're going to try and add some layers onto this and hopefully emphasize how this starts to tie into your periodic table. Keep in mind, folks, the big picture, what we've discussed, we have 4 scientists, Dalton, Thompson, Rutherford, Bohr. We have protons, neutrons, and electrons, and we can figure out what element it is based on the number of protons. If you add protons and neutrons, you get the mass number, which can be averaged to get your average atomic mass. This is the big picture message I'm hoping you'll take with yourselves. Thank you so much for your time. I wish you a wonderful weekend. Have a fabulous, fun Friday. Go and smile at someone that you don't know in the hall. Scare them and be the presence that warms their day. You've had a great day, I hope. See you soon. Bye-bye.
Cool to get smile.